Okay, hello everyone. Thank you for coming to another weekly webinar on gravity. Today we are very glad to have with us Miguel Zumalacarregui. Just as a brief summary, to let you know, Miguel got his PhD in the Autonomous University of Madrid in 2012, and afterwards he went as a postdoc to several places like the University of Heidelberg, the Nordic Institute of Theoretical Physics, and the University of California, where he was a Marie Curie Global Fellow, joined with the Institut de Physique Théorique in Saclay in France. And now he's back in Europe as group leader of cosmology in the Astrophysical and Cosmological Relativity Division of the Albert Einstein Institute in Germany. Miguel is well known for his works in scalar tensor theories and modified gravity, and in particular the applications of these theories to cosmology and to astrophysical observables. Today he will talk about this topic, I believe, in particular about gravitational wave lensing beyond Einstein's general relativity. So Miguel, thank you very much for being here, and it's your time.
Thanks, Mario. It's a pleasure to be here. I hope some other time I can visit in person. Yeah, thank you very much. Today I'll be talking about test of gravity with gravitational waves, and specifically a novel framework for gravitational wave lensing. I guess I don't need to motivate this too much for this audience, but the starting point for my work is that and for this type of test is that we have a very strong motivation to search for new physics that have an effect in cosmology. Because on one hand, we have a very successful description of the universe, the lambda CDM model, which nonetheless has 95% of its energy today in unknown components, dark matter and dark energy. And because the otherwise very strong evidence for these components is indirect, it relies very heavily on our understanding of gravity and the properties of GR that are assumed in the analysis. It's a very fair question to ask: how much can we trust general relativity? By the way, can you see my pointer?
Yes, we can.
Okay, great. And also, please feel free to ask questions at any time. So yes, we want to be sure that we understand gravity, and therefore the properties we infer for these components of the universe are correct. But also another interesting motivation is emerging because even though lambda CDM fits most observations, there are some data sets that are entering into tension with one another. For example, different measures, direct or indirect, of the Hubble parameter, how fast the universe is expanding, have come to disagreeing values. So in blue is the direct measurement using supernovae calibrated with Cepheids, which gives a high value around 74 kilometers per second per megaparsec, and then the early universe, which is really Planck cosmic microwave background and baryon acoustic oscillations, which gives a low value of about 67, and these are at over 4 sigma significance currently. So we want to come up with alternative explanations that might solve these tensions, and we also want to come up with different methods to test those explanations and also test this, measure this independently. For example, gravitational waves is one way to independently measure the Hubble constant, and although now the error bar is huge, in the future it might help determine whether one of these other measurements has some problem with it, or whether there are systematics or new physics. So it's a good time to be excited because we have now gravitational waves that have been on for a couple of years, but it's really ramping up. So in the latest observing run of LIGO and Virgo, and only in the first part of the observing run, there were 39 new confirmed events. So this is a very strong upgrade with respect to the previous observing runs in the few years before. And this is something that's going to continue in the future, where there's going to be more like improved sensitivity and also more detectors that will allow more tests, better localization, and so on. And then in the roughly a decade from now, a little longer, we will also have LISA in space, observing gravitational waves at lower frequencies, and also a next generation of gravitational wave detectors, where the amount of events will be incredibly high. We're talking hundreds of thousands or millions of events. Now, on the cosmology side, I would argue that the future is no less exciting. There is a new array of next generation experiments that have either begun operation, like the dark energy spectroscopic instrument, or are going to start soon, like the Euclid satellite or the Rubin survey, previously known as LSST. And these new observations of large-scale structure and galaxies will bring a lot of information, and among other things, we can expect 1 to 2 orders of magnitude improvement in how well we can test gravity. And I would argue that this is a conservative estimate. So there's a lot of progress to be made. And there's also a lot of progress to be made in combining the knowledge from these two fields, so gravitational wave astronomy and also more classical cosmology and large-scale structure. So I'm going to be talking mostly about gravitational waves. As you know, test of gravity with gravitational waves. There's a lot that one can do with how gravitational waves are emitted, and this is something that LIGO does routinely. But I'm mostly interested on how gravitational waves propagate through the universe, how they the universe and also the large-scale structure in the universe affect gravitational wave propagation, and how can we turn this into a test of ER. So this talk, I'll briefly give an overview of theories of gravity, then I'll discuss propagation on the average universe, just for some background, and then I will present the new result on gravitational wave lensing. So let's go to theories of gravity. I like to remind people that if you look at the dictionary, gravity is not just the force or the phenomenon that many of us spend a lot of time thinking about, but it's also the quality of something being very important or serious. And I think this is it's actually very appropriate, because gravity is linked to a lot of the open problems in physics, which you can, there is a very good compilation in Wikipedia on this link. And these problems involve things like the cosmological constant problem, the origin of the universe, things that properties of singularities and black holes, things that involve gravity very directly, and also things that involve gravity less directly, like the problems of dark matter, the nature of dark matter and dark energy. As I mentioned before, gravity is connected to our understanding of both. So the hope is that by studying different theories of gravity, one might gain inspiration into some of these problems. There's also the issue of, we want to have alternatives to the standard cosmological model, and a cosmological constant in particular. So for example, inflation, I think, is a very suggestive of at least considering dark energy models different from lambda, because we had an accelerated expansion era in the early universe that was not caused by a cosmological constant, because it ended, and because from the initial power spectrum, we know that the expansion rate was changing with time. And there's also the issue, of course, of the tensions. So if the tensions in lambda CDM get verified, then we need to change the model accordingly, similarly to how when lambda was introduced after supernovae observations in the late 90s. And well, independently of that, we also want to test gravity for the sake of it, because in my opinion, the level of trust we have in Einstein theory should not come only from the beauty of the framework and how much we like it, but also from the increasing number of competing theories that are now rolled out as more and more tests have been enabled. So, and yeah, forgot to mention that there's these lambda CDM tensions. There are some attempts to solve them using modified gravity. This is an example from a paper I wrote a year ago, where changing the effective Planck mass at early times can release, partially at least, the tension between early and late universe measurements of the Hubble rate. This is not I would not call this a good solution. I would call it a step in the right direction, and there are other attempts, but I think it's something to keep in mind. So that's the why. Then let's consider how. So general relativity is a very unique theory. There are the theorems by Weinberg and also Lovelock that tells us that Einstein's theory is the unique theory of a massless rank 2 symmetric tensor representing the metric. So in order to make progress, we can break some of the assumptions in this theory, like, for example, allowing Lorentz, breaking Lorentz symmetry, or we can make the theory, make the metric massive, and then Weinberg's theorem is not valid anymore, and this will lead us to the Ram-Kavadatze and Tolles theory. But the most popular way to do it, which is also connected to many of the other ones, is just by adding new ingredients of the theory, adding new fields. We can add another fundamental tensor or more, leading to bigravity and multigravity, which are related to massive gravity. We can also consider vector fields, and in most cases, most popular kind of alternative that people have considered is adding scalar fields. Theories with a scalar can be classified into Horndeski models, which contain most of the examples that you might be familiar with, like Brans-Dicke, F of R, Galileans, Gauss-Bonnet, etc. And also, but there are also theories beyond Horndeski that have been studied in recent years. So now let me go to establish the basics, go to describe some of the effects that can happen in, before talking about lensing, let me consider a homogeneous universe. So imagine that all these large-scale structure that we know exist, we forget about it, we just average it out, and then gravitational waves propagate very trivially. We can think of them propagating on a straight line between the source and the detector. But nonetheless, different theories of gravity will will cause some modifications on the gravitational wave signal. And there's basically just a handful of effects that we might have. And you can convince yourself of this by writing the equation for tensor transverse traceless perturbations of the metric on a homogeneous and isotropic background. This is, of course, I'll be focusing on Lorentz symmetric theories, and that there are some assumptions here, of course, but you can basically change the speed, you can change the damping term, the coefficient of the first derivative, you can add what would be a mass term, and you can then, if you have other fields, you can have interactions with them. So let me start with the speed. So, and to understand these terms a little better, let's think of, just forget about the time dependence of these coefficients. Let's think of plane waves, put them back in the equation, and then we can obtain dispersion relations for the frequency, and express the corrections that come as an amplitude, as either an amplitude or a phase. So if we modify the speed, the change in the dispersion relation is exactly that, is the speed. And because it's real, it's going to be a modification of the phase, and it's also frequency independent. So this changes the speed of gravitational waves. And because it's frequency independent, the change, we need an electromagnetic counterpart to measure this change in speed. This happened a couple of years ago with the detection of gravitational waves from neutron star merger, and then less than 2 seconds later, gamma ray burst. I'm sure you've all heard about this. This places phenomenal constraints on the speed of gravitational waves, which were very stringent on a number of theories. So some of us had worked on this, and before this happened, and of course, when the rumors of the event were inevitably leaked, many of us were started working on chasing the ambulance and outlining the consequences. And oddly enough, there were 4 papers, at least 3 papers on the same day, like simultaneously on the archive, and 2 of them with the exact same name. The one by Paolo and Filippo, and the one that Jose Maria and I wrote had the same name. And the reason why so many people rushed to do this is because there were a lot of theories that predicted that were cosmologically interesting and viable. For example, here I'm showing some models that had were able to feed data at the time without a cosmological constant, but they gave this very strong deviation in the speed of gravitational waves by as much as 20 or even 50%. So this was a very strong rebuke of this type of theories. And this was very constraining. We can go back to this diagram of theories and see what kind of models predict or can predict a modification of the propagation speed. So for example, here I'm showing in dark the theories that are constrained. It doesn't mean that the whole theory is ruled out. For example, in Lorentz violating theories, there's usually one or maybe a couple parameters that are very constrained, and the rest of the theory is unaffected. But overall, this completely rendered useless a lot of theories that were complicated and led mostly simple theories, some non-trivial survivors, and of course massive gravity, where we have a change in the speed of gravitational waves, but it's a change that is given by the mass. So this just places a constraint on the mass of the graviton. So yeah, the next thing we can have in this modified equation is the friction. We can change the friction term. And because this is a first derivative with respect to time, we get an imaginary contribution to the dispersion relation that will be seen as a change in the amplitude. So it's a change in the amplitude, and it's frequency independent too. So this is something that I'm not going to discuss it in more detail, but it needs to be, you also need an electromagnetic counterpart to constrain it. Then going further down, there is the possibility to have a mass term, which then again changes the phase. So it's real, so it changes the phase. And because it does not depend on k, when you compare this with the speed term, this gives a frequency dependent correction to the dispersion. So it's a phase correction that is frequency dependent, so it can be tested using gravitational waves only. And finally, there's the possibility that I'll discuss now of having additional degrees of freedom that propagate and can interact with the metric polarizations. And this broadly, I will call it gravitational wave oscillations. It's not as simple as this insert a plane wave, because then you need to consider two plane waves, but it modifies both the phase and it can modify and the amplitude, and it can be frequency dependent too. So the idea here is that we have a theory in which the matter is coupled to this Hij metric. So gravitational waves are emitted by this in this basis. But because there is this interaction, the way gravitational waves propagate is as a combination of both Hij and these F additional degrees of freedom, which is basically the same that happens in the phenomenology of neutrino flavor oscillations. So that we have an interaction basis and a propagation basis. They're different from each other, and then what the result of this is that gravitational waves are emitted, but a fraction of it goes into the in the propagation basis in this Fij, say dark metric, if you want, and then the fraction of missing amplitude of gravitational waves is given as a function of the theory parameters, and then it has a modulation that depends on the mass, the distance to the source, and also the frequency. So this can produce interesting frequency dependent modification that can be tested by LIGO with black hole mergers, and could also be detected by LISSA with higher precision. And here, this is an example from one of the LISSA papers by the LISSA cosmology working group, where we looked at the effect of the gravitational wave amplitude of having these oscillations with, I think the mass is around 10 to the minus 25 electron volts. So this, to recap, well, there are this series of effects. We can think of them as if we think of a derivative expansion, this speed is at leading order in frequency or wave number. Then damping has 1 power of the frequency, so it's subdominant, and then the dispersion is 0th order in frequency, and this determines the properties. And then oscillations requires that there are additional degrees of freedom. Something to notice is that this combination of order in frequency and frequency dependent tells us what constraints are stronger. So the speed of gravitational waves is very strong, because it's even though it's frequency independent, because it's a phase effect that accumulates with propagation. Whereas this damping is not very strongly constrained, because it's an effect of the amplitude, and the amplitude, as you know, in gravitational waves, we measure it much worse than the phase. Whereas the other effects that involve frequency dependent modifications are very well. I mean, one can argue that these are very, very good bounds for, and this is because there are phase effects that are cumulative with the propagation of gravitational waves. So any questions? This is the first part of the talk. Well, and sorry, just to finish this, it's fairly well understood how different theories of gravity produce these effects. And the reason, well, is there is this, we can look at this texture-coded diagram of the different theories. If you're interested, you can find more details in the review I wrote with Jose Maria Esquiaga. So any questions? All right. So this was all for gravitational wave propagation on a homogeneous universe. So forgetting about large-scale structure, now let's see what happens when we include the possibility of having gravitational lensing. And here, gravitational lensing, I'm going to take it to be as general. You can think as generally as you want. So it can include weak lensing, strong lensing. It can include having a big mass near the environmental effects, like a big mass near the source, a big mass near the detector. It's really propagation on an inhomogeneous background. And the reason to study this is, for instance, electromagnetic lensing of electromagnetic radiation is a very strong probe of a very robust probe of gravity and other new physics like dark energy and dark matter. But when it comes to test of GR, at least for theories that are minimally coupled to the metric, it's kind of very limited because it only probes the geodesics of the metric, and it therefore only probes gravity indirectly through the gravitational potentials. So if you want to come up with say that a test where you only probe gravity, you need to constrain the properties, the relationship between these gravitational potentials and the matter distribution using different observations. Now, I think it's also good to go beyond the Friedman-Robertson-Walker propagation, which is it's already well understood, and it's not. I don't think there is much more in terms of framework that needs to be done. Whereas if we break the symmetry of this of the background, we can get a lot of new interactions. For example, this coupling between derivatives of the scalar field perturbation and derivatives of the metric mediated by background. Sorry, this would be the background scalar field in a scalar tensor theory. And this is something that is goes beyond this FRW solutions where the scalar and tensor perturbations decouple from each other. And finally, gravitational wave lensing. So with electromagnetic signals, we have a lot of observations. We have observed very special systems like this smiley cluster of galaxies that is very cute. But with gravitational wave events, we're nowhere near that, but we're in the right path. So because there are more and more events, there's going to be a lot more detections that will allow us to probe deviations from the average universe, and in particular find the analog of these strong lens signals in gravitational waves. And this bears new opportunities to test gravity. So, okay, that's all great. The reason why this has taken a while to do is because it's actually a very hard problem. So we need to combine modified gravity, which comes with complicated equations, with gravitational waves, which means that we need to worry about the gauge fixing, and there are a lot of tricks that are not that cease to be valid when we go combine modified gravity of gravitational waves. Like we cannot fix the residual gauge to set the trace of the metric to 0. And also we are interested in gravitational lensing. So the background is inhomogeneous, and we have all these new terms that would vanish in Friedman-Robertson-Walker and mix the everything together, all the equations together. So I like to draw the analogy of this being like working, like doing science while taking care of your kids during a lockdown. And it's actually me a year ago working on this paper while my son took a nap with me. So it's tough, but and there are other complications too. Like in principle, gravitational waves are very low frequency, so we might need to worry about wave optics corrections if the frequency, unless the frequency is very, very large. And here, this is an example of these wave optics effects on a LISA source, where you can see at high frequency there can be a diffraction pattern, and at low frequency there is no magnification because effectively the size of the gravitational wave is bigger than the effective size of the lens. So in order to make this possible, we had to go do some simplifications, and in particular we used a frequency expansion. So this whole thing of the wave optics is not an issue anymore. So Now, here's a sketch of what happens in gravitational wave lensing beyond GR. So we have a source, emits gravitational waves, and then these gravitational waves can come closer to a lens. And if in modified gravity, if we have certain deviations from general relativity, we have the same issue as in as we had in for gravitational wave oscillations, and which the interaction eigenstates, so the metric and the additional fields are not the same as the propagation eigenstates inside of the lens. So we need to find these eigenstates to solve the equations of motion, and the effect overall is that these eigenstates can travel at different speeds, and then after they cross the lens, there will be an imprint on the detector from these different propagation speeds here. So in a little bit more detail, the calculation goes as follows. So we start with the 10 components of the metric and the scalar field, and we arrange them in a vector of fields, which we then perturb. So there will be background quantities, which I will put a bar on, and then there will be this delta test perturbations. And then for each of the perturbations, we expand it in a WKB fashion, where there is a phase and an amplitude, and the phase, this epsilon coefficient is small. The phase is varying very rapidly, and then the amplitude is computed perturbatively. And on top of that, there is this there's a polarization vector, which is a combination of the metric components and the scalar field. Then we need to fix the gauge, which we're going to fix the Lorentz gauge, which can be done in general. Solve the constraint equations, and this is this gives algebraic relationships between the propagating degrees of freedom and the non-propagating degrees of freedom. So, for example, in this theory, in the presence of a non-trivial background, the non-propagating degrees of freedom, for example, the trace of the metric, which in GR we can often set to 0, it's given by contractions of the propagating degrees of freedom, like metric polarizations and the scalar field perturbations with different background quantities, and usually involving scalar field. So these solving these constraints produces 3 equations for the 3 propagating degrees of freedom. And here's where I'm going to stop at leading order in epsilon, which is epsilon to the -2. So 2 derivatives acting on this phase factor. And the structure of these equations is that there are 2 derivatives. So everything is a box operator. There are 3 equations that are in general mixed. Here I'm making some assumptions about some of these coefficients being 0, some of these coefficients being equal to each other. But this is something that we found later in a specific example. So it's general enough to be interesting and simple enough that we can solve it in a relatively simple way. So the coefficients of these equations are box operators, so second derivatives that are characterized by propagation speeds, and there are 3 of them. There are in this case, there are the speed of the metric perturbations if there were no scalar field, the speed of the scalar field, and then there is a mixing between the one of the metric perturbations and the scalar field, which is characterized by an amplitude called mixing coefficient and a speed of mixing here. So in order to make progress, we need to diagonalize this. So go to Fourier space and diagonalize this. This is, by the way, assuming we've normalized the perturbations so that there are no extra coefficients in here. And well, you can see already, so we diagonalize this. One of the the metrics is, the way I've written this, one of the perturbations is decoupled. So one of the eigenstates of propagation is pure metric, is in this case the cross polarization, and travels at the speed that we would naively assign to the metric perturbations. But there is another propagation eigenstate that it's a combination of the the plus metric perturbation and the scalar field. And so it's if this mixing is small, it's mostly given by the plus polarization of the metric, but it has a small contribution from the scalar field perturbation, which is proportional. At leading order is proportional to this mixing term and also to the difference in propagation speed between the different terms. So this term mixes the metric and the scalar field, and it also this mixing also changes the speed of this mode, even if it's slightly. There is a change in speed that's proportional to m squared, and then another factor there.
Miguel, sorry.
Yeah.
Hi, can you hear me?
Yeah, hi, Marco.
Okay, hi. Can I interrupt you? Can I ask a question now?
Yeah, please.
So I was wondering about the diagonalization. So you can do it only if all the coefficients are constant. But do they are constant?
They are not. They depend on the. So we only looked at spherically symmetric sources. They are not. They depend on the position, and they depend on the
on
the
time
direction.
also, no?
Yeah, the time dependence we're neglecting. This is something we didn't have the stomach to do that.
Okay, so but even with the space dependence, so how do you diagonalize this matrix then?
We diagonalize it locally. We do it locally, and then we compute the total phase as appears as an integral on this of this speed when we compute the observables. So it's a local. Remember, we're doing a high frequency expansion, so everything is it's local, and then the problem would be to match the amplitudes later. So there would be some difficulties to deal with in the next order.
Okay, so at this order that you consider them as constant, basically.
Locally constant,
yeah.
And then the result for the time delay is an integral over so solving the geodesic equation. If you solve it perturbatively, as I'm not gonna get into details, but I can show you in the next slide. Then the solution is an integral over to compute time delay, which is the observable. It's an integral, and then you can you just need the difference in speed locally at each point in the lens.
Okay, I see. Oh, thanks.
Yeah, no problem. Any more questions? Okay, so there's this additional effect of the mixing between the scalar field and the metric, and there is the converse effect. So similarly, the scalar perturbation, the true propagation eigenstate is it carries a little bit of the metric perturbation, and similarly, the speed of the scalar field is going to be modified slightly with respect to what it would have been in the absence of this mixing. By the way, this mixing, this M5 coefficient, is given by the spatial derivatives of the scalar field. So this is something that vanishes in Friedmann-Robertson-Walker, and this is why we need to consider gravitational lensing or inhomogeneous spacetimes to do this, to obtain this type of effect.
Miguel, sorry, one question. Maybe I missed some assumption, but in general, since you are expanding around an anisotropic background, you're also going to have some anisotropy in a sense that you see what I'm saying. So are you assuming that there is a residual isotropy in the propagation?
No, and in fact, the speed of gravitational waves depends on the direction.
Sorry, I didn't see it. Okay. Sorry.
No, it's it's the propagation is inhomogeneous and anisotropic too.
Okay.
And in fact, yeah, please.
Sorry, related to this, is it also? I mean, it's not obvious that you don't run into instabilities like that. The speed of sounds are positive. So is it possible that you enter into some unstable regime?
So it could be. So I was wondering about that too, because well, you know your own work, of course. So in principle, if these coefficients are large, the speed of sound square could become negative. Mm-hmm. And I don't know if this is equivalent to the instabilities of the like gravitational wave induced instabilities in the scalar sector. I'm not sure if that's equivalent, but it could happen.
No, it's probably not equivalent in the sense that here you have a scalar background and an inhomogeneous scalar background, but of course at the end you're always testing whether the small perturbations are healthy or not.
Right. Well, it could be. Yeah, you're right. It could be. I mean, complementary to that in that mm-hmm. sense. Mm-hmm. In any case, well, I have in mind very small modifications. So mm-hmm. in the theory that I'll explain in a minute, this did not happen. But in more dramatic situations, it could, and it's definitely something to look at for, like, say, scalar induced instabilities on gravitational waves. Okay, so and any more questions about this? Okay, so so there are these three states, and of course we also have the electromagnetic signal that may or may not be emitted from the same event. So we end up with 4 signals, of which we can extract 3 time delays. And these signals, in general, they'll have different speeds. So the phenomenology is very similar to birefringence of light in a complex material, where the speed can depend on the position and the direction of propagation. So just as you can see in this picture, there's going to be different speeds leads to different deflection angles that we explored, but I'm not going to discuss it in the next 5 or 10 minutes. But we have this time delay. So there's in principle the time delay between the electromagnetic signal and one of the metric polarizations, which we call the multi-messenger time delay. And the one I'm going to focus on is, however, which is the most novel one, is the time delay between the 2 metric polarizations, which I'll call the polarization time delay. And now, going back to Marco's question, the way we compute these time delays, well, there is a geometric component, but there's also a Shapiro component, which we assume that the deflections are very small. So we take a straight line, and then we integrate to get the time delay, the Shapiro time delay, we integrate the inverse of the speed, so this quantity. And this is why, at least in this Born approximation and this perturbative expansion, you only need, because it's an integral, you only need the local value of the speed of gravitational waves. And this, of course, is missing small corrections that are proportional to the deflection angle, so that they should be small. Right, so this is something we have. In general, this time delay, so we have a gravitational wave, it's emitted, crosses a gravitational lens, there is a time delay that is larger than the sensitivity, the time resolution of the detector, but it's small, then we can start seeing subtle effects. So here in the top panel, I'm showing the amplitude of the 2 the plus and cross polarizations, which are roughly given by the the two metric, the pure metric and mostly metric eigenstates. And you can see here in the bottom the difference with respect to the GR signal as this would be seen in the detector. This, of course, depends on a lot of things, and in particular, it depends on the orientation of the source with the detector. So this is for very specific antenna pattern. But you can see that if the time delay is small, so 5 milliseconds, there is a subtle imprint that may or may not be, might be degenerate with some of the binary parameters. It might be within the detector uncertainty. But if we increase the time difference, so this is 50 milliseconds, then there are some more dramatic effects. So for example, there's this some time before the merger, there is some destructive interference between the two polarizations, and then there is more distortions, and then most importantly, there are basically two copies of the merger and the ring down happening. So it's I believe that this is a very clear signal, at least in this intermediate range. There could be a very dramatic modification of the waveform. And then if the time delay is longer than the duration of the signal, as can be observed in the detector, then what we have is that the signal is split. So we have two copies of the two or more copies, perhaps, of the same signal that will have, in general, different amplitudes caused by the antenna pattern and the inclination of the source, and also will have different polarizations. So this would look like it's a more subtle prediction, but it would look like different signals that are related but have different, we would identify it as having different distance to the source and probably also different inclination angles. So this is a more subtle effect that would be in principle possible to search, but hard to do. So how long do I have?
Say around 5 to 10 minutes, maybe.
Okay, great. I'll try to finish in 5.
More 5 than 10.
Okay, more 5 than 10. So I just wanted to show an example of, because this is so far has been very abstract and very generic, but this can be computed. These are things that can be computed for a specific theory. So I took Horndeski theory, where there is I think I'm missing a canonical kinetic term, but there is a coupling between the field and the Ricci, and there is also a derivative coupling. And this is a theory that is very constrained by the changes in the speed of gravitational waves and on a homogeneous background. So I'm going to keep this constraint into account, but still there is in principle the possibility of having a strong still an effect that is detectable. And here is this is the time delay. In blue is for between the electromagnetic and the metric signal, and in red is between the two metric polarizations. And you can see that they have different time dependence. Yeah, for this we can compute everything: deflection angles, Shapiro time delays. But what I wanted to show, this is a plot with the parameters of the theory in both axes. So the farther to the bottom and to the right that we go, the more GR the theory is, the smaller the parameters. This is a suppression scale. And the gray area is what's ruled out by the observation of a neutron star merger and the cosmological constraint. But using this multi-messenger time delay, we can, for a heavy mass, so this is 10 to the 10 solar masses, we can go even farther. For example, the multi-messenger, sorry, the polarization time delay would allow us to, can in principle allow us to exclude the orange region. but we need a very heavy and very dense lens. In practice, this is very very unlikely to happen from a random lens in the line of sight, but this could very easily happen if there is a source of gravitational waves that is very near a compact object, say a supermassive black hole, like in a hierarchical triple system. And this is kind of a scenario that has received a lot of attention following the event 1905-21, which was in the mass gap and had a possible, although not clear, not pristine electromagnetic counterpart. So if we can find events of this type in the future, then we're in a situation where it's precisely that. There's a lot of matter very close to the source, and this could create this type of signature. This type of lensing events is not very good for Horndeski because it's very constrained, but this would be very good for theories with derivative interactions in which the cosmological speed of gravitational waves is equal to the speed of light. And there's a bunch of theories like that, like multiproca theories, where there are multiple vector fields that cancel the cosmological modification of the speed of gravitational waves. Then a gravitational lens would spoil that kind of adjustment, and this could be a very strong test for that. So let me conclude. I hope I've convinced you that there are good reasons to study and test gravity. In my humble opinion, with respect to Friedman, Robertson, Walker, we've understood it fairly well. There are a number of tests. They're useful. They're definitely going to improve, but they're not going to improve dramatically. Whereas gravitational wave lensing, it's pretty rich in terms of phenomenology. You've seen that at the very leading order, there are some some effects that potentially can be very clear. No need for an electromagnetic counterpart, and might be very constraining. But of course, there's a lot to do, both in terms of searching for these effects and using them to constrain theories, and also extending the framework to higher orders in this WKB expansion. And perhaps the main overarching conclusion is that speed of gravitational waves, so probes that are fairly standard are even boring for lambda CDM, like the speed of gravitational waves, can be very constraining for non-standard scenarios and allow us to test different theories. And let me finish with yet another definition of gravity, which in this case, there is gravity is modified, changes in time, and these changes can be measured and have very important implications. Thank you.
Thank you very much, Miguel, for your nice talk. Okay, so we have some time for questions. If anybody want to ask something, just unmute yourself.
Hi, I have a question. Well, thanks all. Thank you for the nice talk. I mean, mine is a very naive question. So some of the theories that you consider in the Horndeski class have nonlinear effects, screening effects, and are you assuming something about that? Because if I understand well, you have in mind lensing by supermassive black hole, which is probably in a very dense region inside an AGN. And would that make any difference if you had screening for what you...
It's a very good question, and I omitted it completely. But we are taking screening into account. I don't have a plot here, but to compute this kind of predictions and these plots, we are taking the screen solution around we've taken symmetric lenses, right? So only spherical symmetry, but we're taking the screen solution. And in this theory, what we find is actually interesting, is that these effects are sizable up to the vertical line is the Weinstein radius. So these effects are sizable within the Weinstein radius, even though of course, this theory is the coefficients are very suppressed, so the Einstein radius is much smaller than we're used to. But yeah, it's taking into account.
So you're saying the effects, so this difference between the speeds of the various eigenstates is important even inside the Einstein radius.
Yeah, so there is a subtlety there because we have not, we have considered this theory as is, like a very small modification of gravity, where you would, I mean, the change on the speed of gravitational wave is 10 to the minus 15. I imagine the post-Newton correction to post-Newtonian parameters are of the same order. So it's not, you don't really need screening. So in this case where you don't have screening, you still have that the gradient of the scalar field around a compact object is, or a very dense mass, is very suppressed because of these nonlinear interactions. In this sense, you have screening. Now, what is true is that if you, on top of that, you had a term, say a cubic Galilean, a term that is not suppressed, that it's does not change the speed of gravitational waves, does not cause trouble, but has a much larger coefficient in front, I think that would suppress these effects down, and that's true. That would be one way in which this is suppressed. But I think though that suppression, my guess is that it would be most important near the so deep within the Einstein radius, but all the plots I've shown, for example, this is for a source at the as far as the Einstein radius. So there might be some suppression here, but at the Einstein radius, this suppression should go. The suppression factor should go to unity or close to unity, so it might not be that dramatic. It's really devils in the details. I think we were lucky with this theory that we studied what seemed like the simplest theory, but I think this might be also a lucky choice. We haven't looked at different powers of this derivative coupling. There's definitely a lot of details that could change and might spoil the detectability.
I see. Thank you.
The other thing that I glossed over is in this scenario. So this is a conformal coupling to the Ricci. So this would not couple to a black hole. So in order to have this this type of observational situation, you either need to be sourced by the matter around the black hole.
Exactly.
That might not be enough, or you need to modify the theory further. So
yeah, although if you're in an AGN, you probably have lots of matter around, right? Disk. Yeah. Oh, but that's nice. Thank you.
You're welcome.
Okay, I think there is another question by Sebastian.
Yes, can you hear me?
Yes.
Okay, well, first, thanks, Miguel, for this nice talk. I have a question regarding the echoes that you were mentioning in the beginning or in the middle of the talk. Are they basically a single echo that comes from the two different polarizations like here?
Yeah, so that's a good question. So if there is one lens, there should be just one. Well, let me be more precise. So there's one echo from the there's one echo induced by one lens between the two metric polarizations, right? Which is what I've shown here. You could have another echo if the scalar polarization is emitted. So you have a third, the mostly scalar polarization could be yet another echo. But it could also, you could have more echoes if there are multiple lenses. So you can imagine if there are two lenses in the line of sight and they're not, and they have an, they're not, so imagine that I am the source and you're the detector. You have two lenses that are not aligned and the gravitational wave passes the two of them. Then each of the lenses could split the gravitational waves into two states. So there could be, the first lens could cause 2 copies, the second lens would double, like split each copy into, so you would have 4 and so on. So if you have many lenses, you could in principle have many echoes. And I imagine then that the amplitude would be diluted between these echoes, so that they might become very hard to observe.
Okay, thanks. Thank you.
You're welcome.
Okay. I have a question.
Okay, yeah, go ahead.
Hi, Miguel. Thank you very much for your nice talk. And my question is the following. Different eigenstates propagate at different speeds. So which of these speeds is the one that we must compare with the LIGO gravitational wave 2017 event?
Well, so if let me go to the equation. So in LIGO, so in the LIGO events, there is no. We're talking about the homogeneous modification, so the average, the modification from the average universe. So what you have there is that this m phi coefficient, which is proportional to derivatives, spatial derivatives of the scalar field, this m phi is 0. So the one you would be seeing is box H. This I call it CH here, and that's the same speed as the pure metric state. As you include inhomogeneities, then you start changing the other speed, the C2. But yeah, for LIGO, the speed coincides with the pure metric state. And something that's interesting is that for Horndeski, so you could have very easily have a theory, if you can construct a theory in which CH is the speed of light. So these diagonal elements are standard, but this mixing speed is different from the speed of light. You could have a theory that is completely unconstrained by the Friedman-Robertson-Walker constraint, but is very strongly constrained by this lensing and environmental effects. Now in Horndeski, which is what we looked at, this doesn't happen. This CM is always the speed of light, but I'm wondering if Lorentz violating theories or other variants, other possibilities might satisfy this property.
Right, thank you.
Okay, so thank you very much, Miguel, again for your talk. I have the video off, sorry. Thank you very much, Miguel, for your talk again.